Hello everyone, this is Dr. Hopkins with a video reviewing the concept of free energy and thermodynamics. So what we're going to talk about in this video is Gibbs free energy, and the basic equation for Gibbs free energy is delta G is equal to delta H minus T delta S. So let's define all the terms in these. Delta H is our enthalpy change, sometimes referred to as heat. Delta H is something that we can measure by calorimetry, so we can directly measure the delta H. And if we had to relate it molecularly, it's related to bond formation, bond breaking, intermolecular force formation, intermolecular force breaking, any of those direct energetic interactions. That's what enthalpy, that's included in the enthalpy change. Delta S is the entropy change. Okay, now entropy change is not directly measurable. It is there's no such thing as an entropy meter. And it's sometimes referred to as related to the disorder in a system. Basically, you have higher entropy, the more ways you can set up some system. The less ways you can arrange a system, the lower the entropy is. It's a little bit more esoteric concept than delta H, a little harder to discuss and relate to actual molecular properties, but it's there. And then we have temperature, which is in Kelvin, because Kelvin's the only scale that has 0 in the right place. And then the last one on here is the delta G, the free energy change. And now once again, free energy is not directly measurable. We do not have a free energy meter. And it's related to the spontaneity of a process. So basically it tells you, hey, if the Gibbs free energy tells you that this process is going to happen, thermodynamics is saying it will happen. And thermodynamics is always correct. All right, so let's look at reaction thermodynamics. So relate this to chemical processes. And remember from last semester when you were doing heat and calorimetry, you can determine the standard reaction enthalpy using sets of formation reactions. There were several ways that you could determine these delta H's, but the easiest one was by formation reactions because there are tables and tables of them. You can Google them. They're in the appendix to your book and so forth. And so the enthalpy change of a reaction is the sum of the enthalpies of formation of the products. Now we have to adjust those for stoichiometric coefficients minus the sum of the enthalpy changes of enthalpy of formation of the reactants, once again adjusted for stoichiometric coefficients. So an example, if we took a simple combustion of propane reaction, and I have it written and balanced, where you're generating CO2 and water. So what we would do is we'd set this up where we would have the heats of formation of CO2, the heats of formation of water, minus the heats of formation of propane, and the heat of formation of O2. And so we set this up here. Now I've got my stoichiometric coefficients. So it's 3 times the heat of formation of CO2, 4 times water, and minus 1 times the propane. You'll notice we do not have O2 in this equation. It's because the heat of formation of O2 or any element is always 0. So we don't have to include that because that zeroes out. And so then we go to a table. I'm not going to show the table. I'm just going to show the values that I looked up. And we found that CO2 is minus 393, minus 285, and then we have minus 103 for our propane. And if we add all that up, we end up with minus 2220 kilojoules. And so that would be the enthalpy of that process. That's something you did last semester. So let's look at reaction Gibbs free energy, okay, so for a particular process. And it turns out that it's analogous to enthalpy, okay, and that we can relate delta G to tables of the delta G's of formation of our products and our reactants, okay, so we can sum them all up. So we'll do the same thing for our same reaction. Now remember, I'm not going to go back and show the balanced reaction, but we had 3 CO2s, 4 waters, and 1 propane. Once again, the Gibbs free energy of formation of an element is also 0, so we don't have to include O2 as well. And so we have all of these values. These are our delta G's of formation. I looked them up in a table. And then I plugged them in. So this is minus 394. We found that water was 237. And propane is 23.4 kilojoules. And we end up with minus 2108 kilojoules. Okay, so for the enthalpy, remember, we could measure that. We could measure the heat evolved. So we could check, oh yeah, I'm getting 2220 kilojoules. But for free energy, we can't. But what does it tell us? Well, the delta G of a reaction, if it's less than 0, that means it's spontaneous. So in this case, we're negative. So it's a spontaneous process. So if you have a delta G that's negative, that means the reaction is going to proceed towards the products. If you have a delta G of reaction that's greater than 0, that means it's non-spontaneous, or what we call non-spontaneous, and it will not proceed towards products. If you started with reactants, you'll still, in the end of basically all time, end up with still mostly reactants. You won't get very many products at all. And the amount of reactants and products depends on the magnitude of your delta G, so depending on how large that value is. But the sign tells us whether it's, so if it's negative, it's going towards products. If it's positive, reactants. So if we summarize everything that we knew from reaction gives free energy, so we can do the same thing with delta G that we did with delta H. We can use tables of formation, reaction gives free energies to calculate our delta G of a reaction. Then if the sign of the reaction tells us if it's favored for products or reactants, the magnitude tells us how far it's going to go. So how many of the reactants are going to convert to products. So depending on the delta G, we may have all of the reactants disappear and just go completely to products. Or we may have all reactants have no products. So the question of will there be any reactants left or how many products will there be depends on the magnitude of delta G. And we're going to use these two principles to develop a concept to mathematically determine. We're going to develop a ratio of products to reactants based on delta G. So that will come about next time.